Hello, everyone. So I would like to introduce myself first. I just got my I got my PhD degree from the University of Tokyo last year, and I attend the Osaka University as an assistant professor. And our core researcher is Mr. Liu, a master student from the University of Tokyo, and Dr. Kikuchi, the associate professor from Shizuoka University, and Dr. Shibanuma, who is my supervisor when I was in the University of Tokyo. And my topic is about the Multiscale model simulation for analyzing the fatigue strength of the austenitic stainless steel with bimodal harmonic structures. So first, I would like to introduce my talk as a 4-part. Firstly, is our research background. We all know that the microstructure have the influence of the fatigue strength. Generally, the smaller grain size will induce in the larger fatigue life and the higher fatigue limit. However, currently that has not been a theory or model to quantitatively explain the influence of the microstructure on the fatigue life and the limit. And our research target is a new designed material with the harmonic structure, which is made by the coarse grain structure and the 3D connected network of the ultra fine grain structure. And this new material can achieve both the high strength and the high ductility. We can see the tensor strength more than 1,000 megapascal. The strength is reached 0.6. However, there's some issues for this new material is that the current research on the HS material is based on the expensive and inefficient experiment analysis. That means we need to perform lots of the fatigue tests to determine the fatigue property, and that has not the numerical model to quantitatively design the fatigue performance of the HS material. Therefore, our research motivation is to propose a multiscale modeling strategy to predict the fatigue life of the HS material and to design the optimal microstructure for HS material based on the multiscale model. And then I will go to the detail of the multiscale modeling simulation. Firstly, I will introduce the two basic modeling concepts. The first one is that we calculate the fatigue life only from the crack growth life, because from our experiment evidence, we can clearly find the micro crack is observed for less than 1% of the fatigue life. So in that case, we can ignore the life of the crack initiation. And the second concept is that we reduce the complicated 3D fatigue phenomenon to the 2D problem with 2 steps. The first step is we assume the crack initial site is considered on the specimen surface. And the step 2 is that the total fatigue life is calculated by assuming the crack growth in the inside plane. So based on these two modeling concepts, we proposed our multiscale model. So in this model, the input data is very simple. It's only required the test condition and the monotonic tensor property and the microstructure. And there are 3 submodels of our multiscale model, and the output data is SN curve. And by using this kind of multiscale modeling strategy, we can perform the parametrical study to determine the different kind of microstructure distribution with the corresponding fatigue performance. Firstly, I will introduce the submodel 1, that is the macroscopic FEA model. And the target of this model is to calculate the relative elastic and plastic strain tensor and define the active zone. And we calculate the cyclical stress-strain relationship by using the empirical formula by Coy, using this formula. And the input data is only in the monotonic tensor strength, that is the yield strength. And we define the active zone as a surface domain, which is large enough to contain all the possible crack initial sites. And then our submodel 2 is the microstructure model. And the purpose of this model is to define the microstructure distribution on the surface plane and the inside plane. And the input data is the microstructure information as I will introduce next. This is the characterization procedure of the microstructure in HS material. We can find HS material has very complicated microstructure. However, we can only use the IPF map from the EBSD analysis, and then to obtain the to simplify the grain as the elliptical, and we can also measure the thickness of the actual fine grain region. This region, the thickness is will be obtained, and also we will obtain the major axis length and the aspect ratio of the coarse grain and actual fine grain. So this is all the microstructure information we need to make our microstructure model. And this slide shows the generation of the reconstructed periodical grain map by using the obtained microstructure with several steps. The first step is to generate the periodical coarse grain and the fine grain region. So I will not go into detail of this procedure, but the final goal is to generate this region. So the coarse grain will be assigned in this white area, and the actual fine grain will be assigned to this black or this light blue area. Okay, so this is an example. We assign the coarse grain in the coarse grain region, and the actual fine grain, which is has the shape of the ellipse in the actual fine grain region. And then to convert this elliptical coarse grain or fine grain to an RPGM, this is a reconstructed periodical grain map. So by using this RPGM, we can generate any size of the grain map because it is the periodical. And so we can go to define the microstructure model. So as I introduced, our goal is to reproduce a 2D spatial distribution of the grain of the HS material in the specimen surface and the inside plane. So this shows the distribution of the grain in the surface plane. So we selected the coarse grain from the grain map and then assign it to the area elements in the specimen surface, because we from the experiment results, we find that the crack initiation will only occur in the coarse grain region. And then we will define the microstructure distribution in the inside plane in this region, inside one. And we obtain the grain map as the cross section of the specimen and define the initial grain, the shape of initial grain as the semi-ellipse. And then based on the relationship of the crack front and the grains in the grain map, we can generate the grain line. So in this grain line, we will calculate all the size of the grains and then to define the average thickness of the grain line. So finally, we can successfully obtain the effective distance of the grain boundary. So this is all the procedure to define the microstructure distribution in the inside plane and the surface plane. And submodel 3 is the crack growth model. And in this model, the input date is also requires the microstructure information and all the predefined submodel 1 and submodel 2. And the basic theory of this model is the interaction theory between a crack and the grain boundary, which is originally proposed by Professor Tanaka and later modified by Professor Shibanuma by considering the physical meaning of the crack length and the slip band length and the effective grain boundary distance. So we can see the input date of this model is the applied stress range and grain size and the friction strength to move dislocation and the crack length. And output date includes the dislocation density, slip band length C, and the crack tip sliding displacement range, that CTSD. And by using that CTSD, according to this equation, we can calculate the crack growth rate DADN by using this kind of form. And this slide shows the procedure to evaluate the fatigue life. Firstly, we assume the crack will initiate as every grain assigned on the surface plane, and then to define the microstructure distribution And by using the interaction theory between the crack and the grain boundary, this kind of theory, we can calculate that CTSD and then to calculate DADM. So we calculate the vertical life of the specimens by using the weakest link principle. That is the minimum number of cycles to failure at all the crack intersites is defined as the final vertical life. Then I will go to show the foundation of a model. We apply the two types of steel. First one is the harmonical material. Another one is untreated material. So we can see the microstructure, especially the grain size, has a large difference of these two types of material. And we perform the fatigue test by using the design specimens. This is the poor fatigue test, and to obtain the two SN curve. And by using our Multiscale model, we can accurately simulate the SN curve compared with the experimental result. So we can find the developed Multiscale model is valid in simulating the fatigue performance of both homogeneous and the harmonical material. And by using this Multiscale modeling strategy, we can perform some material design activities. Firstly, we study the influence of the ultra fine grain area fraction. We design different kind of ultra fine grain fraction. So we can see this is some tendency to influence the fatigue life. And also we consider the influence of the milled powder size. So we also design three kinds of microstructure. However, we find that certainly there's no influence of the milled powder size on the fatigue property. So finally, I will conclude our research. So in this research, we performed the Multiscale model simulation for analyzing the fatigue strength of the Austenitic stainless steel with the bimodal harmonic structures. And we proposed a lower methods to calculate the microstructure features of the HAS material, considering the distribution of the coarse grain and the fine grain. And the fatigue performance of this material was predicted by modifying our previous Multiscale model to extend its application from only homogeneous material to HS material. And the systematical simulation was performed, and a higher ultra fine grain area fraction was confirmed to improve the fatigue life. Okay, so that is all my presentation. Thank you so much for your listening.
Thank you.